Hello and welcome to day 5 and 6 of the advent of code. Okay. The expedition can depart as soon as the final supplies have been unloaded from the ship. Supplies are stored in stacks of marked crates. Because they need to be supplied, because the needed supplies are buried under many other crates, these crates need to be rearranged. The ship has a giant cargo crane capable of moving crates between stacks. To ensure none of the crates get crushed or fall over, the crane operator will rearrange them in a specific and carefully planned steps. After the crates are rearranged, the desired crates will be on top of each stack. The elves don't want to interrupt the crane operator during the process, but they forgot to ask which crates will end up on top where, and they want to be ready to unload the crates as soon as possible. They do, however, have a drawing of the starting of the stacks, and your puzzle input is that, plus the order that the operation will be done. In this example, there are 3 stacks of crates. Stack 1 contains crate Z and is the bottom, and crate N on top, and stack 2 contains 3 crates, being C, M, and D. And finally, stack 3 contains only the crate P. When they are rearranged, the steps are operated, and each step precedes a quantity of crates and from what stack to move that many crates and the stack that they are moved onto. In the first step, the rearrange process, 1 crate is moved from stack 2 to stack 1, a resulting configuration. D on top, then N, then Z on stack 1, CM on stack 2, and P remaining alone on stack 3. In the second step, the 3 crates are moved from stack 1 to stack 3. Crates are moved one at a time, so the first crate is moved. It will end up below the second crate. It repeats this for the remaining steps. The elves just need to know what crate will end up on top of each stack. In this example, the top crates is CMZ, so that's the puzzle input. As you watch the operation be rearranged, you notice that the process isn't following the procedure. Some mud was covering the crane, and you quickly wipe it away. The crane isn't the Chronometer 9000, it's the Chronometer 9001. The Chronometer 9001 is notable for new and exciting features: air conditioning, leather seats, and an extra cup holder, but the ability to pick up and move multiple crates at once. Again, considering the above example, when we move the single crate, nothing changes, but when we remove 3 crates, the ordering doesn't get rearranged. This changes the final result. So instead of being CMZ, it ends up being MCD. Before the rearranging process finishes, update your simulation so that the elves know what they should stand to be ready to unload the final supplies. After the rearranging process is complete, what crates will end up on top of what stack. If we jump over to my advent calendar and go to day 5, this is what the arrangement would look like at the end of the first operation. So LVZPSTTCZ. Originally I had the crates at the bottom, but this required the taller crates to get squished, so instead the crates align with the top and the height of the thing closes. I'm giving this as a visual aid so that when we go through the code, you'll know what's going on where. Jumping over to day 5's code, the usual setup of adding the day on enter and cleaning it up on exit. I then have the crates, which are initialized by loading the crates file and turning them into handles. I then have a ship, which contains the stack, which is a vector of vectors of characters, and then the steps that go through, which is a vector of steps. The steps contain what stack it came from, what stack it's going to, and how many you need to move from each stack. I then have steps being able to be passed from a string, which simply goes through splitting it at spaces and working out what values it needs to pass out. The ship also has a from string, which goes through the first section and checks to see if there's an open square brace in the line, meaning that it must be inside, it must contain at least one crate. It then will extract the crate. If it sees a close, it'll increment the stack by 1 and skip the trailing space. If it finds a space, then it will skip 3 spaces and increment the stack by 1. This is basically just a way of passing out all the crates. It then skips the line specifying which crate stack is which, since that's always 1 through 9. I then go through each stack and reverse them, since I go from top to bottom and I want the stacks to be bottom top. I then create the ship with that stack and a new list of steps. I then go through each remaining line, making sure it's not 0, since this space is separated by one empty line. And I just sort of put error checking there rather than just skipping an additional line. I then go through each step and pass it out, and then put that in the ship. I have an apply steps function in the ship, which takes in a single or not, whether you're doing the first or the second half of the puzzle, which then calls the corresponding steps and the step apply multi-step, which takes in the mutable vector from, the mutable vector to, and the number of steps to make. Using Rust's memTake, I take the from stack out of the vector, and then at the end put it back in. I then also added a function of add step, which just pushes the step onto the stack. The apply step simply pops one out and pushes it onto a second one. This is what rearranges the stack in the correct order by doing one at a time. The apply stack multi uses a separate stack with the capacity of X. It then takes them out in a specific order by popping one, the same as we did with the previous one, and then reinserts everything in that stack onto the new stack. This results in persisting order because we reverse it out and then we reverse it back in. In the read data, we extract the day like normal. We then let our ship equal our ship from string. We then clone our ship so that we can have both permutations of single and multiple applied. We then apply steps as single and apply steps as multiple. We then use our top and top multiple for our 2 output results, then iterate through each stack and take the top character off, checking to see if it's there. This is for testing the examples where there wasn't exactly 9. We then insert that onto our output of top and multi-top. We do that for both ships onto 2 separate stacks, then print them to the console. Then we work out the size of each stack, which is 100 divided by 9, since it is 9 wide. We then create the style for each column, and then the style for each container, and the text style. We then iterate through each stack, keeping track of which stack it is, update the position to being 1 over the stack size, so that each stack is next to the previous one. We then spawn the stack with its specified style, and the children, which is iterating through each container, spawning the container with the container style and the image of the corresponding container, which is what gives each container a different color. And then we specify the text, which is just the container ID to string, center that, and justify center it so that the text ends up in the middle of each container. All right, moving on to day 6. The preparations are finally complete, and the elves leave camp on foot and begin to make their way towards the Star Grove. As you move towards the desired a dense undergrowth, one of the elves gives you a handheld device. He says that it has many fancy features, but the most important one is set up right now is the communication system. However, because he hears you have a significant experience dealing with single-based systems, he convinces the other elves it would be okay to give you the one malfunctioning device. Surely you'll have no problem fixing it. As if inspired by comedic timing, the device emits a few colorful sparks. To be able to communicate with the elves, the device needs to lock onto their signal. The signal is a sequence of seemingly random characters that receive one at a time. The device receives one at a time. To fix the communication system, you need to add a subroutine to the device that detects the start packet marker in the data stream. The protocol used by the elves that the start of the packet is indicated by a sequence of 4 characters that are all different. The device will send your subroutine a data stream buffer, your puzzle input. Your subroutine needs to identify the first position where the 4 most recent received characters were all different. Specifically, it needs to report the number of characters from the beginning of the buffer to the end of the first of such 4 character marker. For example, in the following data stream, the first 3 characters can't have the bit because it has to be at least 4 characters. Then once you've found the 4 characters that don't repeat, you need to specify the next character. So in this example, it is the 7th character, since character M is the 7th character, resulting in 4 characters that don't repeat. It then gives more examples you can test on. Okay, your device communication system is correctly detecting the packet, but it still isn't working. It looks like it needs to look for a message. The start of message marker is just the same as the start of packet marker, except it consists of 14 distinct characters rather than 4. And then it gives more examples of where that position is in the previous 5 examples it gave. If I go back to my advent calendar, I just have a visual representation of where that is. So this is what my start message packet looked like and what the message start packet looked like. It's just a sequence of bars, and their height represents what character they were. Jumping over to day 6 code, we do the simple startup of a day, initializing it and setting day 6. We then have a function called contain dupes, which goes through each character in the string with its index, and then checks to see if the string starting one further than that character contains that character. This is a function that will always guarantee to find the system in, I think it's of log n time, since each character doesn't need to check itself. It only needs to check the remaining characters, and those characters don't need to check the characters previous, because we already know that they don't match. If it finds a character, it returns true, and then if it doesn't, it just returns false. Then we load day 6's data in our passing data. We set up our shutter, which, because part 2 was 14 long, we make a shutter that's from the start of the input string to character 14. We then say our start of packet is at 0 and our start of message at 0, since we know that both of those are in valid positions, since the earliest the packet can be is 4 and 14 respectively. We then iterate from 14 onward in the data structure, each index, and then we check to see if the shutter from 0 to 4, so the first 4 characters of shutter, contain duplicates, and that start is not equal to 0, in which case we set start equal to I minus 10, since we start at 14 and we only want the first 4. And we make sure that start is equal to 0, since that means that we don't overwrite our shutter with a later occurrence of 4 non-simultaneous bytes. We then if contains dupes in shutter, and then set the message equal to I. I was printing the shutter for testing purposes. And then we break, since once we've found the shutter, we no longer need to keep looking. And then, or once we found the message, and then we set the shutter equal to the data of I minus 13 and I plus 1 range. So we just shift it over 1 basically. We then check to make sure we did find the start. Again, just some error checking. and then print out our start and finish positions. To draw that pattern on the screen, we set up the parent with its corresponding style of being 100% of the width and 80% of the height. We then set up our bar height, which is 100 divided by 28. This is just so that the bars don't end up off the bottom of the screen ever so slightly, because we're 150 pixels from the top, which means it is possible that 85% can result in a slightly off the bottom of the screen. The size is then calculated as bar height and then 1/18, since we have 18 values that we want to represent. So the width is 100 divided by 18. We then go through from the start -4 to the start indexes, and we spawn a child with that percentage value of the days, data, bytes, then we get the nth I, unwrap that, convert it to a U8, subtract A from it, cast it to a float, and then times it by the bar height. Very complicated. But that's where we set the position of each bar. This results in an overall height correctness. And then for the message, we do the same. We subtract 14 and iterate through to the message, and it's exactly the same code again. And that is how we represent the signal coming in. And I hope this has helped you out if you've got stuck on this particular day. So like, comment, subscribe, and I'll see you in the next episode.